Okay, quiz 15.4 is on Le Chatelier's principle. Oh, there we go. Question 1 is going to concern this reaction. NH3 aqueous plus H2O liquid will be in equilibrium with NH4 plus aqueous plus OH minus aqueous. Of course, that's the weak base reaction of ammonia with water. And we've got a series of different actions that we'll take to perturb this system away from equilibrium. And Le Chatelier's principle says that the system will respond in order to restore equilibrium, and that response will be in opposition to whatever change we introduced. It will undo, to some extent, the change that we did in order to push the system away from equilibrium. So the first one we have here is to remove some hydroxide through a precipitation reaction with strontium 2+. The strontium's just giving the details of how, but if we remove hydroxide here, then the system is going to want to replenish the hydroxide, and so it will shift to the right. Okay, the next one is if we add ammonium nitrate salt to the solution. So ammonium is right there as a product. Nitrate is pretty irrelevant, but the ammonium is a product, and so if we add ammonium nitrate, that's going to increase the ammonium concentration, and the system will respond to undo that by shifting left toward the reactants. The next one is to place the reaction solution in contact with high pressure NH3. Well, we remember by Henry's law that if we have the amount of volatile solute that is dissolved in water is going to be proportional to the pressure of that solute in the gas headspace above that solution. And so by putting the solution in contact with high pressure NH3, that will have increased the concentration of NH3, and the system will respond to decrease that concentration by shifting it to the right. Okay, so these next two steps, wrong way. The next two steps are a little bit more tricky. The first one is to dilute the reaction solution to 4 times its initial volume. When you perform a dilution or a concentration, then we need to consider the number of moles of aqueous species on either side of the reaction arrow. Or if you do the same thing with a gas, it would be the gaseous species that are important. So we have only 1 mole of aqueous on the left side. Water does not count. And we have 2 moles of aqueous on the right side. When you perform a dilution, then the reaction will shift toward the side with more moles. I like to think of it that when you dilute the solution, then there's more room for everything. And so the aqueous things, because there's more room and more space, they're going to break apart and like take up more space by becoming more molecules. So that would shift it to the right to dilute it. And then the next one is to boil away most of the solvent. That would have the opposite effect. That would reduce the volume. It would concentrate all of the species present here. And that would shift it to the left. And I like to think of that as the molecules are getting crowded. They don't have as much space anymore, and they realize they can sort of relieve some of that crowding by converting from 2 particles to just 1. You can think of squeezing them together until they come together. Of course, those are really non-physical, kind of nonsensical metaphors, but they get the job done. And of course, this is based in mathematics. If we have the concentration of NH4 plus and OH minus on the top, and the concentration of NH3 on the bottom. Let's think about what happens in that first example if we dilute everything. If we dilute everything, then then we'll no longer be at equilibrium, right? At the moment of dilution, this will become a Q, and let's say we dilute it to 4 times the original volume, like the question suggests. We'll divide this number by 4, we'll divide this number by 4, and we'll divide this number by 4. Well, 2 of those will cancel out, and we'll be left with 1 division by 4. That means that Q will be less than K. In fact, Q will be equal to exactly 1/4 of the value for K, because we divided by 4 there. And if Q is less than K, then it needs to shift to the right. That's why a dilution is going to shift this reaction to the right. And then if we do a concentration, I didn't give you a number, but let's suppose we concentrate everything to 2 times its original concentration. Then we'd be having 2 times the ammonium concentration, 2 times the hydroxide concentration, and 2 times the ammonia concentration. Again, 2 of those will cancel out. We'll be left here where Q is greater than K if we concentrate the solution. And if Q is greater than K, then it'll need to shift toward the left. So it really is all based in math, and the equilibrium expression still must be obeyed. And so as we double the concentrations of everything across the board, because we have a different number of products than we do reactants, that will affect the overall reaction quotient and force some sort of a change to re-establish equilibrium. Okay. Now let's move on to question 2. I keep going the wrong way. So we're going to consider this reaction here. C3H8, this is a gas, plus 5O2, that's a gas, in equilibrium with 3CO2, that's a gas. And we're running out of room here. I think we'll just make it 4H2O, and that's a gas. Now, delta H of reaction here is negative 2044 kilojoules per mole. The fact that it's negative means this is an exothermic reaction, and so we can add heat as if it is a product. And again, heat isn't really a product in the same way that these are. They're not going to be producing a certain number of grams of heat or a certain pressure of heat in atmospheres. Right? Heat isn't exactly the same as the rest of these products. And the real effect that changing the temperature will have is mathematically beyond the scope of this course. It would involve a change in the actual value of K, the equilibrium constant. However, we can abstract away all of that complexity and just use this neat little trick where we say for an exothermic reaction, we put heat as if it is a product. An endothermic reaction with a positive delta H would put heat as if it is a reactant, and now we can treat temperature changes just like dumping in or removing product or reactant if it were endothermic. Okay, so now we've set the scene. The real question is, this reaction is highly product favored. If you wanted to produce C3H8, this is called propane, from carbon dioxide and water, say you're an industrial chemist and you want to produce and sell propane to your customers, it's an equilibrium reaction, so that should be possible even though it's product favored, but you're going to want to sort of maximize the amount of propane you get out. So what pressure and temperature conditions should you use? What can we do to drive this reaction as far toward the reactants as we can? in terms of temperature and pressure? Well, for the temperature, as long as we were just talking about that, heat is written as if it's a product. In order to drive it left, then we'll need to add heat, or in other words, increase the temperature. So you want to run your reaction at high temperatures. That will tend toward giving you more propane at equilibrium. And then for the pressure, we need to count the moles of gas. Here we have 1 plus 5 is a total of 6 moles of gas on the reactant side. And 3 plus 4 is 7 moles of gas on the product side. So how do we drive it to the reactants? That would be at high pressures. Higher pressures will shift it more and more to the left, toward the reactant side. Okay, and question 3. So this question says we have a certain gas reaction. It has colorless reactants and dark brown products, and that's all we're going to tell you. That's all you really need. We can just say we have something colorless in equilibrium with something brown. And I actually have an actual reaction in mind when I wrote this question, but you don't need to know what it is. The reaction has reached equilibrium, and it's in a transparent piston, so you can observe the color. And that piston has a movable head, so we can play with the volume and change the volume. If the reaction begins colorless but turns brown as you reduce the volume by pressing down on the piston with high pressure. So what does that tell us? If we have a higher pressure, which way did that shift the reaction? From colorless to brown, higher pressure shifted it to the right. And so this tells us that delta N is going to be less than 0. Or in other words, we have fewer moles on the right and more moles of gas on the left. Now you don't even know what the reactants and products are, but you at least know one simple fact about the stoichiometry, because when we increase the pressure, it shifts to the right. That means that there are fewer moles of gas on the right side. And then you decrease the temperature while maintaining that reduced volume, and the reaction again turns colorless. And so lower temperature shifted it back to the left. Right? We decreased the temperature. If we decrease the temperature, that's as if we removed heat. And so the reaction should shift to the side where heat belongs. We'll write heat here as a reactant, right? I lowered the temperature and it shifted left. And so that means that delta H for this reaction is greater than 0. This is an endothermic reaction. An endothermic reaction. We don't know the magnitude of delta H of reaction, but I think that for a couple of quick observations, you can tell a few decent facts about this unknown, mysterious reaction.